Lab 5, Latches and Flip-Flops. I'm Tim.
And my name's Stephen.
And we're here to present. Next slide. SR latches, the concept of a latch circuit is important to creating memory devices. The function of such a circuit is to latch the value created by the input signal to the device and hold the value until some other signal changes it. Next slide, please. The NOR latch. The SR NOR latch is bistable and capable of storing information passed into it. This SR latch is ideal as it does not require a powered input in order to produce a powered output. If both S and R are disabled at the same time, however, the gates become uninitialized at the same time, causing an oscillation. This is why inputs of 1 and 1 are typically avoided. Next slide, please. The NOR latch. The Q output is triggered by the S rising input, or rising S input. As defined earlier, an input of 1, 1 can produce an unstable or invalid outcome. The state of Q did not change when S was passed a value of 0, showing that the value was stored. When the R is 1, the value of Q becomes 0, resetting the latch. Next slide, please.
So now the NAND latch. The SR latch utilizes 2 NAND gates to be able to set and reset content. Unlike the NOR latch, the 0, 0 state of the inputs produces 1, 1 on the outputs, as can be seen in the image. The input S outputs to the output Q2 down in the bottom corner, whereas R outputs to Q2 not. In this latch, the output value will always be the same as the input value, except when the inputs are 0, 0 or 1, 1. When inputs are 1, 1, the outputs will be inverse to the first input to reach the corresponding NAND gate, as can be seen in this truth table. As can be observed in the timing diagram, Q outputs are triggered only on a falling edge. This can be seen above here.
The gated D latch. You can write or store a 0 or a 1 bit in this latch circuit by making the enable input high or a 1 and setting D to whatever you want the stored bit to be. When the enable input is made low or 0, the latch ignores the status of the D input and merely holds the stored bit value, outputting the stored value of Q and its inverse on output Q naught. Next slide, please. Looking here at the transition table, we can see that when the gate is 0, the Q plus will be the same as the Q input. That is, the output of Q is going to be the same as the input of Q. When the gate is 1, the Q plus will be the same as the D input. Next slide, please. And we can see that here with the waveform. If we look at the Q input, we can see that when Q is low, we also have D going low. When we see that Q is high, D is also high. Next slide, please. And here we have the Latches sim drawing of the gated D latch. Next slide, please.
So now we're going to get into shift registers. This was not technically one of the gates that we had to produce for the labs, but it was one that we were asked a lot of questions about and was present a lot in the readings. This flip-flop can be used to create a series of loadable registers of size n. A series of flip-flops wired together is known as the shift register. In the provided example, data can be passed on a falling edge through the D0 to each flip-flop in the serial array. Muxes control the direction of the data flow, and we'll go into a demonstration here in a moment. As you may recall in one of the questions, we had one about 4 D inputs and serializing that data through the inputs. This is an example of a 4-bit shift register. We'll do a demonstration now for each function of the shift register real quick. So I've got here my shift register. This is the 1-bit one. I'm going to quickly demonstrate the functions here. So 0, 0 is left. We obviously don't have any values, so I'm going to place one right here, which is there. So if I was to press the clock value, it moves to the left. If I was to make this a 1, it will move that to the right. So let's go ahead and trigger that a few times, and you can see it moving along to the right. Similarly, I can turn that off and make it go all the way to the left again and clear it off the screen. Now, the other thing is clear, which obviously will set everything to 0. So let's first set them both to 1. And if I turn this off, they're all reset to 0. So that's the setting all to 1 and setting all to clear. So I can demonstrate that those hold by removing both of those, and demonstrate again that those stay as a clear when you do that. So let's pass a value through. So let's press the right thing, and as this is still turned on, it will keep passing values to the array, to the shift register. If I turn that off, now there's just 2 values and they will cycle through the object. And this obviously still works in the 4-bit variation. So I'm going to quickly do a 1, 0, 1, 0. Actually, it would be read that way, 0, 1, 0, 1. And if we want it to go left, we just press the clock. And we can see 1, 1, 1, 1. I'm going to turn these off, or just one of them off. And you got 1, 1, 1 and 0, 1, 1. And now we've got them, and they obviously shift through the thing. So that's that. So, and that was it. That's the end of our presentation. Thank you for watching.